All right, welcome to Psych319, Chapter 4, Part 3. So there are several theories of object recognition and how we can identify things in the world. One of them is template matching, the other is feature analysis, and another is prototype matching. And they're very similar, so let's get into it. Template matching is the idea that we compare information in the sensory register, in our senses, to a stored memory, and that the idea in template matching is that it has to be an exact match. If you want to see an object as a chair, it has to be exactly as something you've seen in your memory. The problem with this model of template matching is it doesn't account for a whole bunch of variances in the world. For example, there's a million chairs that you have seen, and there are probably a million chairs that you haven't seen that you can still recognize. And you can take a chair and you can turn it 45 degrees along any dimension, and you'd still recognize it as a chair, even though there is no brain representation for that exact view. And that's a problem with template matching. So again, you can process information and identify it even though you've never seen it before. For example, you know this is probably a chair. Even though you've never seen it before, it's a very unusual chair, but you know that it has enough of the features that you can say, oh, it's got legs, it's clearly a place to sit, they're selling it at a furniture store, so what else could it be? So maybe the idea is, instead of using exact templates, we do analysis of features. Most of you probably say, okay, this is an elephant. Clearly it's an elephant. But if you look closely, there's something completely screwy with the legs, right? Now, if you were to look at any part of the elephant, you would say it's very elephant-like. That's clearly an elephant foot, that's a tusk, the trunk, eye, ear, and so on. And then your brain fills in the rest. It takes all of that information, all of those features, and it says there are enough features for it to be an elephant, and therefore it's consistent with the idea of an elephant, thus it must be an elephant. And this is very similar to how the brain works. We have neurons that are selective for particular features of stimuli, and these features are sort of like the smallest units in language, phonemes. So if you have a certain number of phonemes that are glued together in the right order, like elephant, then you say, okay, well, there's enough features there for me to perceive the word and the idea of elephant. So, okay, I'm going to forget this demo here. Don't worry about it. And so there's evidence in visual search tasks for feature analysis. So if you're asked to look for a target, like in the upper panel, if you're asked to look for a target, a green square, well, if that is embedded in a search array of very different distractor objects like red squares, it's really easy to find that no matter how many elements you add to the array. Boom, 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 boom. The reaction time is consistent with the overall display size. I can add more and more elements, but because the features are incredibly different between the target and the distractor, it's very, very, very easy to pick this out. Now, if you have an array that's more complicated, it might be slightly more harder to find the red square amongst some squares that are also red or maybe slight variations of red, and you might find that the heterogeneity of the search array makes it more difficult to find your target. And in cases where the target is either incredibly similar to the background, or in cases where the background is so distracting that it's hard to find the target amongst all those different features, the target doesn't pop out. Here, it pops out. We call this a pop-out task, because the target is very clearly defined based on one feature. Here, it's not so clearly defined, and so in this case, the reaction time increases with the number of elements you add to the display. But it just shows us that we rely on features quite heavily for object identification and search. And if you think about it, trying to find your friend in a crowd, you're looking for what they're wearing, a red hat, orange shirt, so on and so forth. So another model that falls in with this feature idea is called the pandemonium model. And this is sort of the main model in object recognition. And it's a hierarchical-based model. So rather than saying there's one stop between sensation and perception, we say that there's several. So imagine you're doing some reading and you see a letter and you want to decide what letter that is. And so there's many steps between actually perceiving the letter. Oh, by the way, this silly cartoon, the pandemonium model kind of gets its name in the sense that there's several demons in your brain, and they're all responsible for doing a different task. So here's the big grand decision demon. These guys are responsible for detecting letters, and these guys just detect lines and shapes. So you imagine you have an image demon. An image comes in, and all it merely does is take that image and sends it forward to the rest of the brain. And then somewhere along the way you have little feature detectors, and these feature detectors will tell you, yes, there's a straight line there. There appears to be some parallel lines. There's some curves. There are no continuous curves, like there's no circles in it. So it'll tell you what's in the image and what's not, and then send that forth to the letter demons, and their job is to say, okay, there's some things that are very similar to this image, and all these properties are very similar to like a P and an R, so they're trying to cast their votes very loudly, but there's not very many features consistent with an S. And so these neurons become very, very, very active while these are dormant, and then they send that information to the decision demon, and it has to decide whether it's a P, a D, or an R. But the idea, again, is that we have several neurons in the brain that are dedicated to detecting features. And if they become active, and enough of them become active, then we just say, okay, there are enough features in the image that are consistent with the notion of that letter or that object. And no, we don't actually believe in demons. Again, this is really in the brain, this is implemented as spatial filtering and template matching in the sense that each of these features is matched to something in the image. So how is this implemented in the brain? So you have low-level feature detectors in the retina, lateral geniculate nucleus of the thalamus, and the cortex. The job of these things is to find lines, colors, simple shapes. And then these neurons send projections to the neurons that are selective for letters, and then letter neurons send projections to those that are sensitive for words, so on and so forth. And the competition for distractors is solved by what's called a winner-take-all strategy. Once you decide that that letter is an R, you eliminate all other possibilities. And so the neurons that encode the letter R will actually inhibit the other letters, like P, that are similar to R but not R. So taking this to the final step, we say we have what's called prototype matching. So the brain uses, rather than saying that we match to a template, we match to a prototype. Again, the problem with template matching was that it had to be an exact match. So with prototype matching, it's based on probability. You have what's called in your head a canonical representation. When you think about a telephone, you're thinking of a particular type of phone. Is your phone a cell phone? Is it a rotary phone? Is it a princess, press the buttons, digital phone? What kind of phone is your canonical phone? What is your ideological phone? And it might have a particular color, a shape, and even a particular viewing orientation. Most of us aren't thinking of the bottoms or the backs of our phones. We're thinking of when you're looking at the numbers. And that is our prototype. And so all template matching and feature analysis is compared to that prototype, that idea of what the phone is in your brain. And if a stimulus has enough features that are consistent with the target, then we consider it a match. So again, going back to this, we recognize this as Margaret Thatcher because there are enough features here that are consistent with what we know of Margaret Thatcher, even though this is a bizarre orientation and even though we know these eyes and lips are upside down. So what's really going on? We probably use a combination of feature analysis and prototype matching. Data is analyzed from the bottom up. The analysis of data can be influenced by top-down processes, and when the data is ready for analysis, it's compared to prototypes in memory. If the data is a close enough match, then recognition occurs. Bravo. Somewhere in between the image, the raw image, and your recognition of this as a basketball player, we have all this low-level feature detectors. And I mentioned earlier that we have a bunch of cells in the retina, LGN, and cortex that are responsible for detecting lines and shapes. Well, this is what you might get out of your retina. This might be the output of the retina. The retina's job is really to find colors, even though there are none here, is really to find lines. And it does a very, very good job of that. It has all these specialized cells that can tell the difference between high contrast images, like blacks versus whites, and find an edge. And it tells the rest of the brain, okay, here's an edge. And then another part of the retina and the brain will fill that in with color. And there was a computational scientist who called this the 2.5D sketch. So it's not quite two-dimensional, and it's not quite the three-dimensional representation in your brain. It's somewhere in between. And so your retina finds what we call the zero crossings, the lines of maximal contrast. So here's a maximal contrast, a difference between black and white. And so the retina will draw a line there. And then it constructs this sort of 2D, 2.5D representation, and then it adds color, texture, motion, and depth. And with all that information, you're allowed to do some object recognition. Okay, so let's do a little fun now. We're going to do some, and this will be a good time for a break. I'll take a break here, and then we'll go into the final stage.